Imagine approaching the absolute most extreme object in the universe. Today, we're taking a journey into the ultimate cosmic unknown. We're stepping right up to the very edge of human understanding in this explainer to explore the profound, mind-bending mysteries of black holes. Now, what would happen if you actually crossed the point of no return? It sounds like pure science fiction, right? But the physics behind this are incredibly real. So, picture this. What would actually happen if you were in a spacecraft, flying closer and closer to this giant cosmic titan, and you finally crossed that absolute point of no return? Okay, let's dive right into this. First off, a black hole isn't actually an empty hole in space at all. It's an incredibly dense object. And what's absolutely crucial to understand here is that its power comes from that extreme density, not just its total mass. Think of it like this. When a massive amount of matter gets squished into a tiny, tiny space, it literally warps the fabric of space and time. The gravity becomes so intensely powerful that nothing, not your spacecraft, not interstellar dust, not even light itself, can escape its grasp once it gets too close. So, you might be wondering, if light can't escape a black hole, how on earth do we even know they're out there? Well, telescopes can't see the black hole itself, obviously. Instead, scientists look for what's going on around it, specifically the accretion disk. Because a black hole's gravity is just so immense, it pulls in all this surrounding gas, dust, and, even torn apart stars. But this stuff doesn't just drop straight in, it settles into a flat, incredibly fast-spinning disk. As it swirls closer and closer to the black hole, friction heats this material up to literally millions of degrees. This makes it glow brilliantly, throwing out massive amounts of X-ray radiation. So we can't see the black hole, but we can spot this spectacular, glowing traffic jam of superheated matter right outside of it. And because that accretion disk is so blindingly bright, the invisible black hole in the center actually casts a dark shadow right against it. Back in 2019, an international network of radio observatories called the Event Horizon Telescope hit a massive scientific milestone. I mean, a real game changer. They actually captured the very first direct image of a black hole's shadow in the galaxy M87. It was undeniable, visual proof of exactly what Albert Einstein's math had predicted over a century ago. How wild is that? All right, back to our journey. As our hypothetical spacecraft gets closer to a black hole, the gravity gets increasingly extreme, making a stable orbit way, way more difficult to pull off. But here's the thing. Your experience depends entirely on the mass of the specific black hole you're approaching. Basically, there are two main types we're talking about here. You've got stellar mass black holes, which are maybe 5 to 30 times the mass of our sun, and then you have supermassive black holes, which are millions or even billions of times the mass of our sun. Now, counterintuitively, and this always blows my mind, if you had to choose, you'd actually want to fall into a supermassive black hole. Why? Well, it turns out the smaller, stellar mass black holes have much stronger, far deadlier forces way further out from their centers. Let's break down exactly why that smaller black hole is so incredibly dangerous. It all comes down to something called tidal forces. Imagine you're falling feet first toward a stellar mass black hole. Because the black hole is so dense and you're so close to its center, the gravitational pull on your feet is actually significantly stronger than the pull on your head. Now, here on Earth, we experience tidal forces from the moon, which just gently pull our oceans around. But near a black hole, this difference in gravity is so extreme that it rapidly shifts from a gentle pull into a violent force that physically begins to pull you apart. Which brings us to a very real and honestly, very bizarre scientific term: spaghettification. I know, it sounds totally made up, but this is the genuine astrophysical term for what happens when matter gets subjected to these extreme tidal forces. That immense gravity compresses you horizontally and stretches you vertically. Literally, long before you even reach the black hole itself, you or your spacecraft or even an entire star would be stretched out into a long, thin noodle of matter. But with a supermassive black hole, because it's so physically enormous, you could actually cross right into it before those tidal forces got strong enough to spaghettify you. So, that crucial point of our journey brings us to the most famous boundary in astrophysics. We're talking about the event horizon. This is it, the absolute point of no return. Now, it's really important to understand that the event horizon isn't a solid physical surface like the crust of the Earth. You wouldn't hit a wall. It's an invisible mathematical boundary. But once any object or even a ray of light crosses this specific threshold, the velocity you'd need to escape the black hole's gravity officially exceeds the speed of light. And since nothing in the universe can travel faster than light, anything that crosses that event horizon is permanently trapped, no exceptions. Now, what's really fascinating about this, and this might just be my favorite part of this whole explainer, is that crossing the event horizon actually creates a sort of fracture in reality. It sets up a tale of two entirely different perspectives. There's the distant observer watching you, and then there's you, the falling traveler. This weird disconnect happens because massive gravity warps not just space, but time itself. It's a concept scientists call gravitational time dilation. So if I'm parked safely in a mothership far, far away, watching you fall toward the event horizon, I would actually never see you cross it. As you get closer to that extreme gravity, I'd perceive your motion as getting slower and slower. Eventually, your image would just seem to freeze right there, just shy of the event horizon, slowly fading out and turning redder. But for you, the falling traveler, your local experience of time doesn't change at all. Assuming you somehow survive those tidal forces we talked about, you would just fall seamlessly right across the event horizon, feeling time pass completely normally. But what happens once you're actually inside? Well, at the event horizon, the warping of space and time is so extreme that space-time itself essentially flows inward at the speed of light. Once you're in there, it doesn't matter what direction you turn your ship, every single path leads inward. You and the very space around you are rushing toward the black hole's center, a one-dimensional point of infinite density called a singularity. And it's at this exact point where the incredible mathematics of general relativity just break down and our current laws of physics basically cease to operate altogether. Now, because black holes are just so profoundly mysterious, they've generated a lot of popular myths over the years, and we need to firmly clear those up. Based strictly on the scientific data, black holes are absolutely not cosmic vacuum cleaners. They don't magically go around sucking things in from across the galaxy. In fact, if you replaced our sun right now with a black hole of the exact same mass, Earth would just stay in its exact same orbit. Furthermore, there is absolutely zero established evidence that black holes are wormholes offering handy little shortcuts through space, or that they're magical portals to other dimensions or parallel universes. That's just science fiction. Which naturally brings us to the ultimate question. If it's not a portal, and it's definitely not a wormhole, what actually happens to all that matter after it passes completely beyond the event horizon and heads down toward the singularity? The honest and honestly profoundly fascinating answer is, we just don't know. Because light absolutely cannot escape from beyond the event horizon, our telescopes cannot directly observe what happens inside. Zero information can ever be transmitted back out to the rest of the universe. So the interior of a black hole remains one of the greatest, most compelling unresolved scientific mysteries of our time. It literally represents the absolute limit of human knowledge, a place where our current understanding of the universe just goes dark. And that leaves us with a pretty provocative thought. Will our laws of physics ever evolve enough to pierce that veil of shadow? Or are some cosmic secrets just meant to be kept forever?